Okay, let's continue with linear independence. So for set in vector space, it can be linearly independent and it also can be linearly dependent. Okay, so let set S be any vectors, let's say v1, v2 up until vn. So set S is a set of non-zero vectors. Set S is said to be linearly independent if the linear combinations of all sets in set S is equals to 0 vector. Okay, so this is the form of linear combination, right? So if this value equals to 0 vector, okay, that implies that the C1, C2, and C up until Cn value, the values are all 0. Okay, so since C1, C2 up until Cn are all 0, thus we will have 0 value for this linear combination. So if this happen, that means set S is linearly independent set. Okay, for the next definition, let set S is a set of non-zero vectors. Okay, then set S is said to be linearly dependent if there exists coefficients C1, C2 up until Cn not all 0, such that the linear combinations of all set inside the set S is equals to 0. Okay, so for linearly dependent, there exists value of the coefficient that are not 0. So if the value of coefficient are not all 0, we can conclude that set S is linearly dependent. Okay, so I can conclude that to know the linear independence of a set, we must find out the value of the coefficient such that the linear combination is equals to 0. Okay, jadi kalau you ada multiple vectors, you akan dapat a system of linear equations. So you need to solve the system of linear equations and find out the value of C. And that system of linear equation is a homogeneous system because it is equals to 0. So homogeneous system, you need to solve the homogeneous system and find out the value of C1, C2 up until Cn. If let's say the C values are all 0, you can conclude that the set is a linearly independent. Okay, but if the coefficient, the C1, C2 up until Cn not all 0, tak semuanya kosong, hence you can conclude that the set is linearly dependent. From the system of linear equations, you will have a matrix A. A matrix A. If let's say your A matrix is n by n coefficient matrix, so if the A matrix, the size is n by n, or in other words, A matrix is a square matrix. If A is a square matrix, okay, whose column consists of vectors v1, v2 up until vn, and the determinant of A is not equals to 0. Okay, you find out the value of determinant of A and the value is not equals to 0. This implies that A is non-singular. That means A inverse is exists. Okay, if determinant of A does not equals to 0, then you can conclude that the vectors v1, v2 up until vn are linearly independent. Okay, for linearly independent, refer to the previous definition. C1, C2, the constant up until Cn must all be 0. Okay, for this linear combination. So now our system is A, let's say Ax equals to B because this is the homogeneous system equals to 0. So the B value is 0. So from this, you must solve for X. That means you need to find the C1, C2 up until Cn value. Okay. If this A, the determinant of A, does not equals to 0. That means there exists a unique solution for C1, C2 up until Cn. So that solution will be C1 equals to 0, C2 equals to 0, Cn up until Cn is equals to 0. So all values of C here are all 0. So when all C values are all 0, this implies that the set is linearly independent. You must note that to use this theorem to conclude that the set is linearly independent, you must make sure that the A matrix here, the coefficient matrix, is a square matrix. But if your coefficient matrix, the A matrix, is not a square matrix, you must solve the system by using Gaussian elimination. You cannot use this theorem here. Okay, so let's try this example number 7 of your lecture note. Determine whether set S is linearly independent. So now in our set S, we have three vectors, v1, v2, and v3. Okay, to test for linear independence, we must use this definition of linearly independent. C1 v1 plus C2 v2 plus C3 v3 must equals to 0. So we must find out the value for C here. Okay, C1, this is the V1 plus C2, the V2 plus C3 multiply with the third vector. Okay, and then from here, I will get C1 2C2 minus 5C3 equals to 0. And then the next equation, C1 minus 3C2 plus 7C3 equals to 0. So from this system, I can write this into matrix form. So 1, 2, negative 5, and then 1, negative 3, 7, C1, C2, C3 equals to 0. Okay, because this A matrix, let's say this is my coefficient matrix, matrix A, because this A matrix, the size is 2 by 3, it is not a square matrix. Okay, dia bukan square matrix. So, if it is not a square matrix, you cannot use the theorem here. Okay, because this theorem is only for square matrix, n by n. This one is m by n, the number of rows is 2, the number of column is 3. So now you must solve for C1, C2, and C3 by using Gaussian elimination. To solve this using Gaussian, next step is to transform this matrix form into augmented matrix, and you will get something like this. Now solve this using Gaussian elimination method. So I want to make this element become 0. So this is row number 1, row number 2. So the row operation is negative row number 1 plus with row number 2. So this will give you the new row number 2. 1, 2, negative 5, 0. So we only change the row number 2. So by the way, this is the pivot element, the leading one. Okay, so now apply this row operation. Okay, so this one you will get negative 1 plus 1, 0 here, and then this is negative 2 plus with negative 3, so negative 5. And the next one, negative of negative 5, so positive 5 plus 7, 12. This one is 0. The next step, I want to make this value to be equals to positive 1. So the row operation is negative 1 over 5 R2. So this operation will give you the new row number 2. 1, 2, negative 5, 0. Okay, so 0, negative 1 over 5 times 0 is 0. Negative 1 over 5 times negative 5 is 1. This one, negative 1 over 5 times 12 is negative 12 over 5. And the last one is 0. Okay, step is to solve this system using back substitution. Okay, our variables are C1, C2, and C3. Okay, so C1 plus 2, C2 minus 5, C3 equals to 0. And then C2 minus 12 over 5, C3 equals to 0. Okay, so because we don't have the equation for C3, we just assume C3 to be equals to any constant, let's say T. So when C3 equals to T, C2 is equals to this one, negative 12 over 5 times with T. So 12 over 5T. And then from this value, C1 is equals to, so 5 multiply with C3. C3 is T minus 2 multiply with C2, 12 over 5. T. Okay, so from here, C1 is equals to 5T minus 24 over 5T. Okay, so 5T minus 24 over 5. So 1 over 5T. The solution set for C1, C2, and C3 is C1 1 over 5T, C2 is 12 over 5T, and C3 is T, where T can be any constant, any number. We have infinitely many solutions for C1, C2, and C3. So let's say T is equals to 1. The value of T is 1. So your C1 is 1 over 5, C2 is 12 over 5, and C3 is 1. But what happens if your T is 2? So C1 is 2 over 5, C2 is 24 over 5, and C3 is 2. So infinitely many solutions for this system. So that means not all values for C are 0. Hence, we can conclude that the set is linearly dependent. In other words, there exists a C value that is not 0. Okay, so we can conclude that set S is linearly dependent. For this example, please try this on your own. Okay, and you can check your answer with me. Alright, okay, thank you. That's all for this video.